Okay, so here we are. This is Wednesday noon, and I hear the tornado sirens going off so as per usual, right in the middle of our introduction. But this is what we do Wednesdays at noon. We have special guest speakers, and today we have Glen Harrison, who comes by special request. He is going to tell you a lot more about himself, but particularly about his work as a postgraduate student at the Oak Ridge Research Lab in Tennessee, which is the largest, as I've just learned, science and technology research or energy research lab in the United States. So he's had some pretty unique experiences teaching across the world, in Korea and New Zealand, and as a instructor at LifeQuest, teaching about foreign export and imports, how things get from one place to another, and logistics, and some really unique classes at LifeQuest that pretty much no one else can do but Glen. We also know him as a rowing expert. So he has done presentations about rowing and is particularly involved in the Little Rock Rowing Club. So just very involved in a diverse bunch of topics and subjects, and we're really excited to hear what you have to tell us today about nuclear waste. Thank you, Glen, for being with us.
Thank you. So I'm going to talk today about the logistics of spent nuclear fuel transportation. I'm going to cover several topics here, a little bit about the history of nuclear power, nuclear energy, the logistics of moving spent fuel, what the potential future is for doing that, since we haven't done much of it so far. A couple of examples of actual ongoing programs moving nuclear waste, and then if you're interested in further readings, some literature on that. So for me, this story started when I went to the University of Tennessee and the Department of Geography to work on my PhD. I was interested in geography, but also very interested in transportation related topics. And my dissertation was basically on looking at transportation-related issues regarding spent nuclear fuel. I was fortunate enough, after a few years at the university, to get a graduate teaching assistantship at the nearby Oak Ridge National Laboratory. Oak Ridge is a U.S. Department of Energy research and development lab, one of many around the U.S. It was located there as a part of the Manhattan Project to develop the atomic bomb. But since that time has split off, there is one part of the Oak Ridge complex that still maintains nuclear weapons. But the part I worked at is basically a research and development laboratory. It's like a large college campus, but there's no instruction. It's all R&D. So I worked there as a graduate student, and after I graduated, I was hired on and continued to work there in the Center for Transportation Analysis for many years. So I'm going to talk today about one of the projects I worked on that I think might be of interest. When we think of nuclear power and nuclear energy, many of us go back to some major nuclear disasters that have happened in recent years, particularly 3 Mile Island, Chernobyl, and most recently Fukushima. All involving utility nuclear power plants and releases of radioactive material. But out of these 3 incidents, we also have to remember that worldwide there are 443 nuclear reactors operating in 30 countries around the world, and they've been operating since the 1960s and late 50s. Most of us benefit greatly from this, from our electricity that we get every day. These are the major countries that have utility nuclear reactors around the world. The United States has the most, followed by France, China, Russia, Japan, South Korea, so on and so forth. You can see there the major countries that have that, but the US certainly leads internationally. Electric generation from commercial nuclear reactor plants in the US started in 1958 and has been going on continuously since then. At the end of 2020, the US had 94 operating commercial nuclear reactors generating electricity at 56 power plants in 28 states around the United States. There are 23 plants that are currently in the process of being shut down at 19 sites, again, around the US. Here's a map that shows the location of the nuclear power plants. Most of them, of course, associated with major population centers in the eastern part of the US, and then some mostly along the Pacific coast. Electricity is a major generator. Nuclear is a major generator of electricity in the United States, generating about 20% of our electricity nationwide, right behind natural gas and fairly close to coal. If we look at Arkansas, and I'm sure many of you, as you've driven by Russellville on I-40, have noticed that big cooling tower off to the side of the road there near Russellville. That is Arkansas Nuclear 1, that has two nuclear power plants. Unit 1 began operating in 1974, and Unit 2 began operations in 1980. Arkansas gets about 22% of its electricity from nuclear power, so it's a little more than nationwide, but fairly close. The other major generators are coal and natural gas. So this is a diagram of the nuclear fuel cycle, and it goes all the way from mining to conversion and enrichment of the uranium into fuel rods, placement in the reactor, and then generating electricity. After about 5 years, the fuel rods are taken out of the reactor and stored on site, either in pools or dry cask. And the eventual plan then is to take those reactor fuel, spent nuclear fuel from the reactors, to a repository for permanent disposition. But currently, all that fuel is stored at the different reactor sites around the US. So I'm basically going to talk about the three areas here that are circled in red: the reactor, storage, and eventual disposal. But I thought you might want to just be interested a little bit in where we actually get the uranium for our nuclear power plants. We have some in the US, but most comes from other countries. And as you can see here, Canada, Kazakhstan, Russia, Australia, Uzbekistan, and Namibia provide most of those imports. So nuclear power systems at utility sites in the US are basically made up of two different types of designs. One is the pressurized water reactor, which is a dual system. One system basically interacts with the fuel rods and heats the water in that system, making steam. That then heats up a secondary system of water, and then that water drives the turbine and the generator and creates electricity. The boiling water reactor system basically is a little less complicated. The water that's heated by the fuel rods creates steam and then directly drives the turbine and the generator. So we have both of these systems throughout the utility industry in the United States. The reason why I wanted to touch on these differences is the different size of the fuel rods for these are different, and therefore it is a difference in terms of the capacity and the storage of those fuel rods. So a little bit of history here. The Nuclear Waste Policy Act was passed in 1982, and it assigned the Department of Energy the responsibility for nuclear waste disposal from all the utility reactor sites in the United States. So after this act was passed, Department of Energy went out and started characterizing a number of sites around the United States for this repository site. They did this for about 5 years, and then Congress said, well, we are going to go ahead and designate a site so you don't have to worry about those others. So in 1987, they passed the Nuclear Waste Policy Act amendments that designated Yucca Mountain in Nevada as the geologic repository site for all the utility nuclear waste that had and would be generated. Yucca Mountain is in a desert area, and it's on federal property about 75 miles away from Las Vegas. Well, characterization started on the Yucca Mountain site, and as well as the development of the transportation system starting in the mid-'80s and continuing on into the 90s. Initial acceptance of spent nuclear fuel was scheduled for the 31st of January, 1998. Well, no fuel was ever put in Yucca Mountain. The development of the site continued up until, and the transportation system continued up until 2011, when the Obama administration terminated the Yucca Mountain project and the planning for the transportation system, and set up a blue ribbon panel to determine what we should do with all the nation's nuclear waste generated by the utility nuclear power plants. And that blue ribbon panel has issued a report, and the Department of Energy continues through the Biden administration to do research on the transportation planning, cask design, and repository siting, but nothing definite has been decided as of yet. So this diagram shows the accumulation of the spent nuclear fuel throughout the process. More than 276,000 bundles of spent nuclear fuel have accumulated, which is over 80,000 metric tons of uranium stored at 119 sites in 33 states around the United States. And you can see there on the a diagram of what the fuel assembly looks like right here. Well, the utilities, based on what the federal government told them and the Nuclear Waste Policy Act, basically built storage pools for the spent nuclear fuel at all of their sites. And after the energy capacity was used up in the fuel assemblies, they put these storage they put the fuel assemblies in these storage pools that held the fuel until the federal government would take it over and send it to a repository site. But since that has not happened, then what the utilities have had to do is basically build dry storage casks above ground. And then as their fuel ages, the oldest fuel then gets taken out of the storage pools here and then placed in these above ground dry cask storage facilities on the site of the nuclear reactors. And this continues to be done as more fuel is brought into the storage pool. The oldest fuel then is taken out and put in these dry storage casks above ground. Here's a picture, an example of a real world reactor storage pool, and then some of the dry cask storage systems that are now being constructed throughout the United States at the different nuclear reactor sites at the utilities. This map shows the sites where the spent nuclear fuel are stored, either in pools or in dry cask, or in most cases both, because the pools are just run out of storage space. And you can see at Arkansas Nuclear 1, they have both the pool and the cask, the dry cask storage there. So this map shows the accumulation of the spent nuclear fuel by state. Illinois is the largest. They have the most commercial nuclear utility reactors in the state, and followed by Pennsylvania. Arkansas Nuclear 1 has accumulated 1,623 metric tons of spent nuclear fuel in their storage by the end of 2020, and that is a combination of in the pool as well as dry cask. So with a problem this complex, I'm sure you would agree that we have to have a number of multiple agencies that are dealing with spent nuclear fuel transportation. All of these play various roles. The Department of Energy is the main agency that is going to be eventually taking the spent nuclear fuel and storing it in a repository. The U.S. Nuclear Regulatory Commission approves the construction, the safety and security of the construction of nuclear power plants, as well as the dry cask and the transportation cask that will eventually use to move the spent nuclear fuel, as well as the repository site. So the NRC has a major role in terms of nuclear security and safety. The Department of Transportation is responsible, of course, for transportation safety throughout the nation's transportation infrastructure by highway, by rail, by water. So they definitely play a major role, regulatory role, in terms of the actual movement. The Environmental Protection Agency plays a role in that the development or the building of any nuclear facility for storage has to have an environmental impact statement through the EPA. And of course, our newest cabinet office, the Department of Homeland Security, is involved in security-related issues on the movement of the fuel, as they, of course, coordinate very closely with the Department of Energy in that security aspect. In addition to those federal agencies, state governments are very heavily involved, and there's an outreach program at the Department of Energy to ensure coordination and collaboration with the states as well as the tribal nations. The states are interested, of course, in nuclear safety and security for the power plants that are located in their states, but they're also very interested in the actual transportation system that would initially be developed and used to move this nuclear fuel from the spent nuclear fuel from the different reactor sites across the country to a either temporary or permanent repository. And the tribal nations as well. There are no nuclear power plants on reservations in the United States, but the tribes are very concerned about the transportation system that, again, would move the spent nuclear fuel across their tribal land reservations. And the Department of Energy has an active program to collaborate and provide, get the input and exchange information from the tribal nations. So this shows the major components of the spent nuclear fuel transportation system. Now, these are the components on the ground, not necessarily the system as well, but it's a fairly complicated, expensive system that would eventually be put into place. The utility reactors, of course, have the spent nuclear fuel now. There will be a transportation vehicle fleet maintenance facility to ensure that both the highway and the rail transportation systems that are moving the spent nuclear fuel are in top shape and will safely and securely move the fuel. Then there is a cask maintenance facility that will be in operation to ensure the safety and security of the cask every time a cask goes into operation and moves the fuel. Down at the bottom left, of course, is the transportation system itself, and that would be by rail and highway and a little bit of barge. And then potentially the building of either a interim storage facility above ground and then eventually a permanent repository that would be built below ground. So that is all of the infrastructure that will encompass the transportation system. The DOE, Department of Energy, is both, will be required to acquire both services of the private sector as well as quite a bit of capital equipment for this operation. And on the left there, you can see the services that would be required would include rail transportation from the freight railroads around the US, barge transportation in a very few cases, heavy haul highway transportation, in addition to regular transportation, legal weight truck transportation, Also, they would need to have operation in some of the rail yards around the U.S., as well as cranes for movement of the casks. In terms of equipment acquisition, the Department of Energy would be purchasing the transportation equipment, including rail cars and truck trailers for the movement of the cask, and then the actual highway and rail casks themselves. And you can see example of that down below. We'll get into a little more detail on that here. This is a typical rail cask design, and the preference for movement of the spent nuclear fuel is, of course, by rail. And the reasoning is it's a more isolated transportation system away from population centers. And as you can see down here at the bottom, the capacity of a rail cask is much larger than that you would find of a truck cask. The rail cask here weighs about 125 tons. So pretty substantial piece of equipment. This is a picture of a rail cask that has been designed for operational system. So you would have one or more of these rail casks in a movement from different reactor sites eventually to a repository. This is an example of a truck cask, a legal weight truck cask that would operate and move spent fuel. And as you can see down here at the bottom, it's the capacity for that rail cask is much less, for the truck cask is much less than the rail cask. That's why you want to do as much as possible moving this across the country by rail. And this is an example of the truck cask that would move the spent fuel. So this report, this is one of my favorite reports and quotes out of the report, which basically explains the complexity of the logistics for moving spent nuclear fuel. The report is online. You can download it from the DOE site if you like. Nuclear reactors, materials, and waste sector specific plan. On page 4, it says, because the nation's nuclear power plants were built at different times by numerous vendors using different plant designs, each reactor facility is unique. This impacts the logistics of the spent nuclear fuel shipments. And we found this to be greatly true in the planning for those shipment movements. And in addition to the on-site logistics, you also have the logistics off-site of consolidating the shipments at rail or truck yards, mostly rail yards though, of course, and then moving those across country on various different routes. So I want to look at both of those complexities of both those operations. This shows the loading from a pool into a transportation cask on the left, and then loading from a dry cask onto a transportation cask on the right. So we had the plans when we were developing this for every nuclear utility site across the country. And what we did was basically figure out for each of the sites what the best way and the most efficient way for the Department of Energy to actually move this fuel from the site into the transportation system. The ideal scenario is to move that, is for a rail line to go directly into the cask receiving area where you can load that rail cask directly onto a rail car and then move it out into the transportation system. The next scenario for many of the sites was that there is a rail line into the property of the utility. And this is property controlled and secured by the utility site. In that case, a heavy haul truck is used to actually move the rail cask from the cask loading facility to the nearby rail spur, and then a crane is used to put it on a rail car and then move it into the transportation system. The third scenario was where a rail line is nearby but off-site of the utility. But it's basically the same system that a heavy haul truck is used to move the rail cask from the reactor site onto the location of the rail car, and then a crane is moved to load it onto the cask rail car. The issue here is security. There has to be 24/7 security as long as that rail car and that cask are off the site of the utility operation. So it adds a bit of complexity and expense. The next siting is a local siting that is, again, off-site, and you're moving it, again, by heavy haul. A third possibility, and probably the most complex, was the requirement of using a barge to actually move the spent fuel off the reactor site to a port where it is then moved by crane from a barge onto a rail car and then again into the transportation system. And then the final option is a legal weight truck, which can pull into the reactor loading facility and haul this out. This is very easy, and of course, but you don't get the capacity that you do from a rail cask. The other option, of course, then is to take this legal weight truck and to put it again on, take the cask and put it on a rail car instead of driving it across country like that. So that's the other possibility. So I don't expect you to remember any of that, but what I was just trying to make sure you understood is that it's not like pulling into a gas station, either at an Exxon, Shell, or Valero station, and just filling up your car. The different reactor sites are all truly different and require different logistics for moving that spent fuel out. Now, we're not going to move rail cars one at a time across the country. These require consolidation into multiple cask rail consist to be moved across country. But the reactor sites really don't have the rail capacity to actually consolidate those rail cars. So you're going to have to do that at a commercial rail yard, a Department of Energy facility, or a Department of Defense rail yard. And the DOE and DOD sites are secure. But if it's at a commercial rail yard, then again, you're going to require 24/7 security at that rail yard as long as any of those casks are located there. And one of the planning systems that we did was to locate potential marshaling yards across the country where we might put a consist together and move it then across country. This shows the actual potential transportation system that would have been used from the different reactor sites to Yucca Mountain by rail and by highway and a little bit by barge there. You can see that the rail lines are in red, the highway lines are in orange. But again, if we, this was when we knew Yucca Mountain was going to be the place. Now, of course, all of that is up in the air, but you can see the complexity of the transportation system. And this would have moved about 200 to 300 cash shipments per year across this transportation network. So this is the actual scenario for the transportation network itself. Starts out at the upper left system there with the cask maintenance facility to make sure that the cask is in operational working order. That empty cask is then moved to the nuclear power plant where it is loaded. That loaded cask then is moved to the actual repository or interim storage facility. That emptied. That empty cask then is moved back to the cask maintenance facility for inspection, any decontamination, and then back through the system again. At the same time, the rail car is also taken to a rail car maintenance facility. It is inspected to make sure it is in operational working order, and then it also goes back into the system. You can see down here at the bottom, this is a diagram example of what that rail consist would look like with locomotives, buffer cars in between, a number of cask cars, and then every shipment will have a security escort with it in a rail car. So we're bringing back the caboose for that. So what is the future? So none of this has been done, but there's some potential options. Existing regional utility sites would continue to maintain the spent nuclear fuel in their pools and dry cask. There are some potential proposals to build a temporary facility. Two of these applicants are in Andrews County, Texas, and Lee County, New Mexico, or put a temporary facility at one of the DOE or Defense Department federal facilities. Restart Yucca Mountain Initiative, or locate a new permanent repository, or reprocessing. So I want to just touch on each of these briefly. Here is Lee and Andrews County, and this is an illustration here in the upper right-hand corner of what a site might look like. Again, this is all potential and planning. Nothing has been decided about these sites. Restart Yucca Mountain, it's there. There's been a lot of work already done on it, but in 1911 that was shut down. Finland has made the most progress. They're actually excavating for a repository site for spent nuclear fuel, which will open in 2023. So we could take certainly lessons from them. But they're really the only country that has kind of moved forward on this issue. Reprocessing or recycling, France does a good job at this, and this is the La Hague recycling and reprocessing facility there. Our congressman, French Hill, has advocated for an expansion of nuclear power and reprocessing, and which is ongoing work. While we don't have any reprocessing in the US, that was basically ended during the Jimmy Carter administration. DOE is funding research at different laboratories, DOE laboratories, on the possibilities for reprocessing. And in here, French Hill cites some work being done at Argonne. Now, I wanted to end by talking a little bit about some programs that are actually moving nuclear materials around the country very successfully, and have done it safely for a long, long time. Two of these programs are the Waste Isolation Pilot Plant and the Offsite Source Recovery Program. So the Waste Isolation Pilot Plant, or WIP facility, takes transuranic radioactive waste, which are rags, tools, clothing, soils, and other debris from basically the program to research, maintain, and produce nuclear weapons. That is an underground facility located near Carlsbad, New Mexico. If you've ever gone to Carlsbad Caverns, it's quite close to there. It's a salt formation, and they have taken over 12,000 shipments since they opened in 1999. And the second program is the Offsite Source Recovery Program. It's been going on since 1997. It basically takes unwanted or abandoned or orphaned radioactive sources, and these are from medical facilities, universities, industries, any place like that that has orphan or radioactive material they want to get rid of. And they pick it up for free and take it to Los Alamos National Laboratory in New Mexico and store it there. And you can see Los Alamos there. And every state in the union has taken advantage of this program, and sources have been moved from those locations to Los Alamos for safekeeping. Okay, conclusions. Well, the U.S. Department of Energy continues to study, plan for an interim facility or repository and a transportation system for spent nuclear fuel from utility reactor sites. Spent nuclear fuel continues to remain stored and accumulate at all the commercial sites. For me, this was a little bit of a sad story. I thought we would have this system up and running. The sad story is we haven't yet. The good story is, though, I got my PhD and my dissertation from it. So it was not all bad. So if you'd like to know more about this, there's several sources of information. The nuclear reactors, materials, and waste sector specific plan, and the Blue Ribbon Panel report that was done at the behest of the Bahama administration are both on the Department of Energy website. They can be downloaded. And a very good book on this subject, The Road to Yucca Mountain, was published in 2009, and it's available at the CAL's library system. So that's it. Thank you for your attention. I hope you found it interesting.
Sorry, I was muted. Thank you, Glenn. We are out of time. If you guys want to email your questions to info@lifequestofarkansas.org, we will relay those to Glenn and he can respond to you. We are just privileged to have such an expert to present this topic to us. I don't think anybody else at the LifeQuest staff could have done that. So we have a unique perspective. And I just wanted to ask, is this what you were working on when you were with Homeland Security, this transportation of nuclear waste, or was that something else?
No, I worked on it during early part of my career at Oak Ridge. from the mid 80s through the early 90s, through the Office of Radioactive Materials at the DOE. Yeah.
Okay. Well, again, thank you very much. A very thorough presentation, and we really appreciate your expertise. We have some claps and thumbs up and some responses from Facebook, so hopefully we'll get you some questions. Thanks everybody for joining our special guest speaker series. It's different every week, and we will see you back here next Wednesday for another guest at noon at LifeQuest. Thank you, everyone. Thank you, Glenn.
You're welcome.
Great presentation.